DuckDB under the hood, module 5, run group by on 60 million rows. What does DuckDB actually do? It builds a hash table, one entry for every distinct key. With 15 million distinct order keys, that hash table can reach hundreds of megabytes. And when it grows too large for available memory, DuckDB spills partitions to disk and keeps going. This module walks through exactly how that works. DuckDB under the hood, module 5, grouped aggregation. Think of it like a filing cabinet with 4096 labeled drawers. The 12-bit partition picks the drawer, the 17-bit index picks the slot within it. Each hash table entry uses a 45-bit hash key split into 3 fields. The salt is 16 bits, used to confirm a match without comparing full key bytes. The partition is 12 bits. It selects one of 4096 buckets. The index is 17 bits, the slot position within that bucket. On a collision, DuckDB uses linear probing. It scans forward to the next open slot. This layout is designed to be cache-friendly and to support spilling by partition when memory runs short. When the answer is small, DuckDB can use a perfect hash group. DuckDB knows the cardinality from column statistics. If there are few distinct values, DuckDB uses a direct address table. This means no hashing and no probing. For example, consider grouping by LReturn flag, which has 3 distinct values, A, N, and R. The operator name in the plan is perfect hash group by. This approach is faster, smaller, and has no spill risk. Hash table entries are stored in row major page data structures. The same memory manager is used as the buffer pool, and pages are 32 KB to 256 KB. When RAM is tight, the memory manager spills cold pages to disk. The aggregation operator never deals with spilling itself. Variable length values are stored on separate variable data pages. We attach the TPCH SF10 dataset as a read-only database named TPCH. The attach command completes in a few milliseconds. DuckDB memory maps the file rather than loading it up front. We will use DuckDB memory to track memory usage at each stage of the walkthrough. Let me run explain on a low cardinality group by 3 distinct values of LReturn flag. The scan at the bottom reads the table sequentially. It projects only LReturn flag in the column the group by needs. Above it is the perfect hash group by operator. DuckDB chose this because LReturn flag has exactly 3 distinct values, N, R, and A. When the number of distinct keys is small enough to be known in advance, DuckDB builds a perfect hash function, one with no collisions. Each key maps to a unique slot with a single lookup, no probing needed. The result is 3 rows, 1 per flag, built in a single pass through 60 million linetem rows. Here you see a query against the line item table. It groups by the LReturn flag column and counts the rows in each group. This is a standard aggregation query in SQL. The results show the count for each distinct value of LReturn flag. Now a high cardinality group by 15 million distinct order keys. Let me run explain. The scan reads only L order key, 1 column out of 16 in line item. Above it is the standard hash group by. With around 15 million distinct order keys, DuckDB cannot build a perfect hash at planning time. The cardinality is too high and not known without reading the data. It falls back to a standard hash table. Each new key gets inserted, duplicates get their count incremented. The hash table grows proportionally to the number of distinct keys. At 15 million entries, it reaches several hundred megabytes. If that exceeds the memory limit, DuckDB partitions the input and spills partitions to disk, the same spill path the buffer pool uses everywhere else. Here is the measured gap. 3 groups, perfect hash, 62 milliseconds. 15 million groups, general hash table, 541 milliseconds, 9 times slower. Cardinality does not just change the algorithm label in the plan. It changes how much memory the operator allocates, how many probes it takes per row, and whether the hash table fits in cache. Here's the heavy query, grouping 60 million rows by order key. DuckDB runs this as a hash aggregate, 1 entry in the hash table per distinct order key. With around 15 million distinct keys, the hash table can reach hundreds of megabytes. Next, we check how much memory DuckDB actually used. After the query completes, DuckDB releases the hash table memory. The only non-zero entry is the base table tag at around 241 megabytes. That is the line item data cached in memory from the scan. The hash table itself was much larger during the query. To see the peak hash table footprint, we need to run under a constrained memory limit and watch what spills. You set the memory limit to 64 megabytes. This will force a spill to disk during the next query. The same group by query, now running under the 64 megabyte limit. DuckDB doesn't print a spill message. It spills transparently. The result is correct, but the run is slower because DuckDB has to partition the hash table to disk and merge it back. In the next clip, we confirm the spill happened by checking memory. After the query finishes, DuckDB cleans up the spill files. Memory usage and temporary storage both return to 0. The spill was transient. The key point is that DuckDB spills during execution and recovers cleanly. The output is correct regardless of whether spilling happened. Here's how two-phase external aggregation uses all cores. Phase 1 is thread local pre-aggregation. Each thread reads around 100,000 row morsels into its own hash table. Threads partition entries by hash bits using a 12-bit partition key. Phase 2 is partition-wise aggregation. One thread finalizes each partition. Parallelism scales with cores and there's no single shared hash table. Spills happen at the partition level. Only the cold partitions go to disk. Here's an exercise for you. Given a memory limit of 64 milli, predict whether each query spills. The first query is a simple count star from line_item. The second query selects a L return flag and count star from line_item, grouped by L return flag. The third query selects L order key and count star from line_item, grouped by L order key. The fourth query selects L order key, L linear number, and count star from line_item, grouped by L order key and L linear number. Verify your predictions with DuckDB memory. The answer is in O4 exercise.md. Query 1, count star with no group by. The plan shows a single operator, column data scan. DuckDB reads the row count directly from column metadata. No hash table, no scan of actual rows. This query never spills. Memory usage is constant regardless of table size. Query 2, group by L return flag. The scan reads L return flag from 60 million rows. Above it is the perfect hash group by operator. L return flag has 3 distinct values. DuckDB allocates a direct addressed table with exactly 3 slots. The working set is 3 entries regardless of input size. This query does not spill at 64 megabytes. The hash table is a few hundred bytes. Query 3, group by L order key. The scan reads L order key from 60 million rows. Above it is the hash group by operator. L order key has roughly 15 million distinct values. DuckDB builds a full hash table with 1 slot per distinct key. At 45 bits per slot, that is approximately 84 megabytes. At the 64 megabyte memory limit, the hash table cannot fit. DuckDB spills partitions to disk and merges them on the way back. Temporary storage bytes in DuckDB by memory will be non-zero after this query runs. Query 4, group by L order key and L linear number. The scan reads both L order key and L linear number. The hash group by now groups on 2 columns. L order key combined with L linear number yields roughly 28 million distinct pairs. More keys than query 3, wider key per slot. This also spills at 64 megabytes. The pattern is the same. When the estimated distinct key count times key width exceeds available memory, DuckDB spills. The operator is the same as query 3, only the key count and width differ. The buffer pool we watched in module 04 is the same pool managing these hash pages. The memory manager handles spill for aggregation exactly as it did for raw page reads. In module 06, we'll see the same spilling mechanism applied to sorting large tables. Let's recap. Hash group by builds 1 entry per distinct key using a 45-bit key structure. When cardinality is small, DuckDB uses perfect hash group by instead, a direct address table with no hashing and no spill risk. The buffer pool from module 04 manages hash pages directly. Spilling is transparent. DuckDB partitions and flushes cold pages to disk automatically when memory runs short. After any heavy group by, check DuckDB memory. If temporary storage bytes is greater than 0, DuckDB spilled. Next up, module 06, sorting large tables.